Okay, David, I assume you and Isaac are both on air and amplified, and we can we can go ahead and start the next session.
Okay, Matt, thanks. Yeah, and I can see that we are also live on YouTube. So yeah, let's start. Hello, everyone. Thank you for joining us for the second session of AS AVAR2020. My name is David Alon. I am with the audio team in Facebook Reality Labs. In this session on Spatial Sound Reproduction and HRTF, we have three really nice talks from people who did internships in Facebook Reality Labs, Magic Leap, and Microsoft. So please stay tuned. For the first talk, I am pleased to introduce Isaac Engel from Imperial College in the UK. Isaac will present his talk about listener preferred headphones frequency response for binaural rendering and stereo audio contents, which is basically talking about how users' preference changes with different headphones EQ when playing different type of audio contents. This work was done as part of Isaac's internship with us in the audio team in Facebook Reality Labs, together with myself, with Kevin Scheumann, and with Ravish Mehra. So with that, I would like to introduce Isaac, and Isaac, the stage is yours.
Thank you, David, for the introduction. First of all, can everyone hear me? If you don't, please use the sad face emoji. Of course, if you don't hear me, you didn't hear me say that, but if you don't see the correct slides, do the same thing. Okay, I think everything is good. So yeah, I did this. So this talk, I'll tell you about a study I worked in during my second internship at the FRL, as David said. And we looked into, oh, I see some sad faces over there. Maybe someone cannot see the proper slide.
Yeah, it looks like we're seeing quite a few sad faces, and some of them are coming from the mirrored rooms, I think, because there are sad faces coming from a void in this room that we don't see the person. So I think, Dustin, why don't you go on air for a second, Dustin? Or,
yeah, I'm gonna go check out the other rooms quick.
Yeah, why don't you go ahead and do that, and I'll reset this room as well one more time.
Thank you, guys.
Yeah, I'm really sorry about the delays, but we're trying to get at least a majority of people seeing the slides, and then we just kind of have to press on. So I will reset this space also. Just hold on for a second. So presenters, or I guess it's just Isaac now, please go ahead and select on air and megaphone.
Okay. Anyone cannot see the slides?
Yeah, it still appears that there are some people in the other rooms that are not seeing the slides. We'll wait while Dustin is resetting those rooms also.
Okay. I do see many happy faces now.
So it from my end, it looks like all of the rooms have the correct slides up now.
Okay.
If you do not see the correct slides, please sad face again.
Well, I think at this point, what we'll have to do is proceed, and then if you don't see the slides in another room, please select re-enter space. If you remember, in the menu, go to settings and then general and then re-enter space. And then I think that we just have to move forward with the presentation. So, okay, thank you, Isaac. You can continue.
Okay, so let's start. So as I was saying before, in this talk I'll tell you about a study I worked in during my internship at FRL. And basically, we looked at how listener preference for headphone frequency response may change depending on the nature of the audio content type. For example, whether it's stereo or spatial audio. So the first thing that we need to address here is, why is this a relevant question? And the reason is that headphones, VR headsets, or AR glasses are all used for both spatial audio and stereo playback. And these are two very different use cases. On the one hand, we have spatial audio, whose goal is to make virtual sound sources indistinguishable from real ones. And if we assume an accurate HRTF and room acoustics, or an oral room impulse response, then ideally what we would want is a pair of headphones or headset with a flat frequency response, or headphone transfer function. To achieve these, we usually employ headphone equalization. Otherwise, we could introduce coloration, or we could degrade localization and distance perception in the binaural rendering. Ideally, these equalization filters should be individual. They should be specific to every listener, although generic EQ has also been shown to be beneficial. On the other hand, we have stereo content, which is generally optimized for loudspeaker reproduction. And in this case, a pair of headphones with a flat response may not be appropriate. And it has been recommended to use instead a transfer function that mimics the coloration of an HRTF and a listening room. And on this basis, the Harman target was proposed, which in previous studies has shown to be preferred to other targets such as the diffuse field or free field, as well as several commercial headphones. So the question that we're trying to answer in this study is, does audio content type actually affect the preference of target headphone transfer function? And our hypothesis is that yes, it will affect it. And for spatial audio, we expect the average listener to prefer a flat target, while for stereo, we expect them to prefer something closer to the Harman target. And the way we proposed to test this hypothesis was through a listening test where we evaluate different target transfer functions for both spatial audio and stereo content. And in this way, we can look at the preference ratings for each of the contents and we can compare them. In this study, we focused on the VR headset use case. So with this said, let's have a look at the methods. We chose a Mehra-like paradigm, similar to what has been done in previous studies on listener preference, without a reference stimulus. And as headphones, we used a prototype VR headset with built-in loudspeakers and the frontal part removed so listeners could see through it. And one of the reasons to use this kind of device was to recreate the bandwidth limitations typical of open-ear headsets. As test variables, we had three. First, we had the evaluated target transfer functions, of which we chose 5 that we deemed relevant for the VR headset use case. Then we had the audio content type, spatial audio and stereo. And finally, we had 4 different tracks, including music and speech excerpts. In the next few slides, I'll go through each of these variables in more detail. First, we have the evaluated headphone transfer functions. We chose to use a maximum of 5 of them because we didn't want the test to become too long or exhausting for the participants. And the first ones that we introduced were the ones the literature recommends for spatial audio and stereo reproduction, which are the flat and the Harman targets, respectively. In the case of the flat target, we introduced 2 versions. The one made from individual measurements that were performed on the participants before the experiment, and then one made from KEMAR measurements beforehand, which was the generic one. Next, we introduced what was our starting point, so to say, which is the VR headset without any EQ applied to it. And we expected this target to work as an anchor of sorts, obtaining the lowest ratings regardless of the audio content type. Finally, to bridge the gap between our anchor and the other targets, we introduced a sort of an exaggerated Harman target, which we call 2 Harman, that in preliminary tests obtained preference ratings somewhere between Harman and no EQ. Finally, because we were using an open ear design with a limited bandwidth, as I explained before, we applied a bandpass to all targets to adjust their bandwidth with the reproduction bandwidth of the headset. And these are the final 5 targets that were evaluated in the listening test. Okay. For the second variable, we had the audio content type, which, as I mentioned before, was either spatial audio or stereo. In the case of stereo, we took dry audio tracks ripped directly from CDs, and then we applied different headphone EQ filters to them. In the case of spatial audio, we took the same, we used the same process, except that we added a couple of convolutions in there with a pair of individual BRIRs. These BRIRs were measured on every participant before the experiment, and therefore provided a high quality binaural rendering. If it serves as a reference, a good number of the participants were not aware that the binaural rendering was actually not the loudspeakers playing during the training stages. Oops, there you go, the laser pointer. Okay. And for the last variable, we have the audio material. We have 4 different audio tracks. 3 of them were music tracks taken from our previous experiment, and then an excerpt of male speech of the 4th one. All of them were around 10 seconds long, and in the test, they were played in a loop, so listeners could hear them again and again if needed.
Excuse me, Isaac. I think we have a persistent audio glitching happening, so I'm going to just reset the space one more time. Sorry for the interruption, but I want to make sure people can hear your voice well.
All right.
And then just please reset on air and amplify again once again. Sorry, Isaac.
Yep. Can you hear me any better now?
It sounds great. Yep. Thanks.
Nice. Okay, and everyone can see the slides and the sad faces. Cool. Okay, I'll go on then. So yeah, these were the 3 test variables. Now that we have shown them all, it may be a good moment to hear some examples. So what I prepared here is one of the tracks. In particular, is Bird on a Wire by Jennifer Warnes. And what you will hear next is first the stereo version, and then spatial of the version for 2 different rooms, and finally stereo again for the sake of comparison. Please note that the BRIRs used here may not be yours, so it's likely that this experience may not be individual in the sense of low externalization. And also, we did not apply any headphone equalization because we don't have any control of the headphones you may be using. So depending on the frequency response of the headphones you are wearing now, because you should wear headphones for this example, maybe you will perceive a higher audio quality on one of the 2 content types. For instance, if your headphones are tuned to something like the Harman target or a diffuse field target, it's likely that you would prefer the stereo content in terms of coloration, for instance. But I will leave that to you to judge. So let's hear the examples.
Like a fish on a hook, like a knife from an old-fashioned book. Like a fish on a hook, like a knife from an old-fashioned book. Like a fish on a hook, like a knife from an old-fashioned book. Like a fish on a hook, like a knife from an old-fashioned book.
And then please advance the slide, or the to the next slide. Thank you.
Thank you. Yeah, sorry about that. So on my side, I heard like a slowed down version. Maybe it's because of my internet connection. But in any case, if you couldn't hear it well for any reason, just reach out to me after the talk and I'll send the YouTube link to you. All right. So now that we have heard some examples, hopefully, let's have a look at the actual graphical interface that the participants saw during the experiment. So basically, it was similar to a Mehra test, if you're familiar with it. The participants saw 5 sliders, each one corresponding to the headphone targets that were under evaluation. They didn't know which one was which, and the order was randomized for every trial. And this process was repeated for both audio content types, for audio tracks, and this was done twice for every combination of content and material, which resulted in 16 trials times the 5 ratings. This is 80 ratings per subject. Okay, so this was the experiment. Let's have a look at the results now. What you can see here is data for 21 subjects. On the left-hand side, you have the data for stereo content. On the right side, you have for spatial audio content. The x-axis shows the different target headphone transfer functions, and the y-axis shows the preference ratings. The bars are the marginal means for each of the test conditions, and the error bars show the 95% confidence interval. So we put the data through a 4-way repeated measures ANOVA, and this showed a significant interaction between the audio content type and the preferred target. After that, we ran a 3-way measures ANOVA for each of the audio content types, which showed that for stereo, the Harman target was the preferred one with a statistically significant, it was statistically significant higher than the rest. And for spatial audio, this was true for the individual flat targets, which in a sense is agreeing with our initial hypothesis that depending on the content type, we have a different preferred target. For other observations, we saw that our anchor, no EQ, obtained the lowest ratings regardless of the other content type. And what came as surprising at first was that the generic flat target was not significantly different to the Harman target for spatial audio. And to explain or try to explain why this happened, we did an objective analysis that I'll show to you in a moment. Let's have a look at it. In this slide, you can see at the top left corner a plot with measurements of the frequency response of the experiment headphones after applying generic flat EQ on a total of 30 subjects. The blue line shows the median of the amplitude response across all subjects. The red line shows the target, and the gray line shows the fixed and anti-fixed percentile. So the first thing that you may notice here is that the median measurement, blue line, is actually deviating from the target, which is telling us that KMAR is not well representing the median subject of this population. And this agrees with an observation made a few years ago by Lindau and Brickman. And it's telling us that a better option, or probably a better option to do generic EQ, is to use the median or the average amplitude response of the subject. However, we also observed a high variance
My apologies again, Isak, but the audio was really glitching again, and I checked with a few other people, and so what we we reset, and I think maybe if you back up about 10-15 seconds from what you were saying, if possible, approximately, and then if you can also just go back on air again and go back on megaphone. I don't know if you heard what I just said. I don't think I was on air. Sorry.
Yep. Yeah.
Okay.
So.
Okay.
Yeah, sorry about the glitches. This may be the internet connection on my side. So, yeah, as I was saying, we observed a very small difference between the generic flat target and the Harman target. Is it any better, the audio on my side now?
Yes, it's great.
Sorry.
Yes, much better.
Okay, thank you. And we tried to explain, or we think we can explain this lack of difference through an objective analysis. And in this analysis, we're saying that after measuring the experiment headphones with generic flat EQ applied to them on 30 subjects, we observe a consistent deviation of the median measurement across subjects from the target, which is the red line. And this is telling us that our generic EQ generator KMAR is not well representing the median subject of this population, which agrees with an observation made by Lindau and Brinkman in a previous paper. But more importantly, there was a very large variance in amplitude response across subjects. And this intersubject differences were in many cases larger than the differences between the target curves under test. So what this means is that, for example, for a given listener, the presented Harman target may sound flatter or maybe closer to the flat target than the generic flat. And the sad thing about this is that this is inherent to the generic EQ process, and it's independent of whatever generic EQ generator we use. Even if we use the ideal median subject, this will still happen. But this is the limitation of using generic EQ. Okay, so after seeing these results and these observations, we can conclude the following. First, we observed that audio content type did affect listeners' preference on headphone target response, with the individual flat target being the preferred one for spatial audio and the Harman target being the preferred one for stereo. We did not observe this same effect for generic headphone EQ, and an objective analysis showed a large variance in headphone transfer function across subjects, with the differences between subjects being sometimes larger than the differences between the targets. And this all is telling us that the ideal headphone EQ process should be device-dependent, content-dependent, and also subject-dependent. For future work, we suggest to investigate the effect of the headphones type, whether they are open or closed, and also regarding to their reproduction bandwidth, whether these variables affect the preference of headphone target. And it would be also interesting to repeat a similar evaluation without the extreme cases, for instance, the individual flat target obtaining very high ratings for spatial audio, or the no EQ anchor obtaining very low ratings for both contents. If we eliminate these extremes, maybe we can emphasize the differences between the targets of interest. With this, I conclude the presentation. Hopefully, you have been able to hear most of it. I will take any questions you may have now. Thank you.
Thank you, Isaac. And yeah, I think we have a couple of more minutes for questions. So if anyone is interested in hearing more, please raise your hand.
You should be able to see a raise your hand icon on the right-hand side of your screen, and I'll take questions in the order I receive them.
So
Any
I guess we
questions,
could,
or should we move on?
yeah, I guess we can use the next 5 minutes for taking some rest. Let's thanks again, speaker. Thank you so much, Isaac. I don't see Stephen Crawford yet. So Stephen, if you can hear me, please please come closer to the. Oh, Remy, are you presenting the work here?
Yes, I'm actually presenting, yeah.
Oh, okay, great, Remy. So let's wait for 4 more minutes until we hit 2:30.
Hello.
Hey, Richard.
Remy, does that look like the correct slides on the screen?
You look so angry.
Yes.
Yeah, great.
I'm going to set up my browser here. So
Hey, Isaac, nice talk.
Thank you. Yeah, I think my Wi-Fi was not working very well. Whoops.
Your
I think
Wi-Fi
I'm
has
on there.
some issues, yes. The results, on top, especially for me, were choppy.
Yeah.
Like...
Yeah, I'm not really sure how
Isaac.
many people are actually watching. Yep.
Sorry, sharp. I wanted to say. Can you talk? Doesn't look like. When is your talk, Rishab? Only one. I was about to get a second. Sharp just asked me how much beer I already had. Sorry. All right. Ah, that's nice. This could be a nice talk, actually. Stop eating. Yeah, of course. Otherwise I would wear glasses, maybe. Oh, we are not
Hello?
muted. Ah, hi. Now I can hear you.
Yeah. So you didn't know you were unmuted and you were talking?
Sorry?
That's what. You didn't know you were unmuted and you were talking? That's dangerous.
Yeah, I saw. You're right. And we are here in a group having private conversations on top.
So since we reset, Remy, you might just want to check that you are still on air and amplified your voice.
Nice session.
Okay. Can you hear me okay? Oh,
Yep.
let me put it on. Can you hear me okay now?
Yep, sounds good.
Yes.
Okay.
Sounds good. So let's start, Matt.
Let's see, what is it?
The process signal in our case is the output, or I should say impulse response of our rendering system. So if you're trying to render a sound at a given point in space, you measure the impulse response of your rendering system when it's trying to render that location, and that's the system you're measuring. In terms of the perceptual transform, we're simply doing an FFT and looking at the magnitude response in dB. And then in terms of distance computation, we'll look at two different approaches. The first one is an elastic net, which is a regression approach. And the other one is the Jensen-Shannon distance, which I'll refer to as JSD. This comes from the probabilistic information theory, and I'll explain those two approaches now. So first, the elastic net regression. This is, again, it's a regression, and we're using a cost function that incorporates both the component of the L1 and L2 norms. This has the advantage of producing sparsity as well as grouping. The output of this is or vector beta, which includes the coefficients representing the load of each predictor on the test HRTF. Another way of saying that is you could think of this as a way to project the response of your system onto the HRTF database that serves as a reference, and you're getting coefficients that would let you linearly recombine those HRTF to recreate this full system's output. The other distance measurement, again, is the Jensen-Shannon distance. This is a measurement of similarity between distributions. And so what we do is we measure the similarity for, again, we take a given position in space we're trying to render with the system. We take the response of that system and we compare it to each of the HRTF in the database. And for each one, we get this distance measurement. The more statistically the distributions are, the smaller the distance. So if they are identical, you would get 0 essentially. So I will illustrate with some specific examples, and hopefully that will help describe a little better what's going on here. So let's take a kind of a textbook example. So we take a binaural rendering system that uses a virtual speaker array. We will, for the HRTF filter, we'll use something that's publicly available. So I use the KU100 head HRTF filters from the Cydia database. For panning between the virtual speaker, we will use VBAP, again, a well-known method. For the actual virtual speaker layout, we will start with a cube with a speaker at each corner, which is common method people use, but we'll modify it a little bit by adding a few speakers, and you'll understand why. We'll put one on each side of the head at 90-degree azimuth, 0 elevation. And by the way, this looks like a cube, but those are actually all at the same distance from the listener, so it's really more a sphere, but just for illustration purposes. And then in the front, we put 2 virtual speakers, one slightly above ear level and one slightly below. And this, you'll see later in the example, has the advantage of having an actual virtual speaker at 90-degree azimuth, for instance, whereas in the front, we're panning between virtual speakers, which will help illustrate. This is another view of the same information. Each white square on the map shows you a virtual speaker. Azimuth is the x-axis, elevation is y, so you can see, I'm pointing on my screen that you can see here, but I grab the pointer here. You can see the 2 speakers that are slightly above and slightly below ear level in front of you, and then the 90-degree, minus 90-degree, and then the corners of the cube. So first, let's compute the elastic net method for computing distance. So what we do is we create a sort of a heat map, which represent those beta coefficient I defined earlier. So it's the load of the output of our system on each of the HRTFs in the database to recreate the output of our system. And the maximum is actually marked as black just for easier reading. And out of this heat map, if you will, we will extract 2 measures, 2 mean opinion scores. The first one, which will be the angular distance between the centroid of this distribution and the intended location we're trying to render. So that hopefully gives an idea of the accuracy of the localization in terms of position. And then the other metric we'll look at is the standard deviation of this distribution. And this is likely going to be indicative of how we may perceive the source as being diffuse or compact, for instance. So this is the same data, just with a bit of smoothing, but I plotted on top of that the circle. And here, to illustrate the specific example, we're trying to virtualize a source in front of you. So 0-degree azimuth, 0-degree elevation. And it turns out the centroid of the distribution here is actually aligned with that position. So we have a MOS 1 of 0 degrees, which is indicative that magnitude response in this case is unlikely to introduce a bias in terms of position. And then for MOS 2, we look at the standard deviation of this distribution. And there we get a value in this example of 14, a little over 14 degrees. And this could potentially be interpreted as an indication of the impact of magnitude response on the compactness or diffuseness of this rendered virtual auditory image. This is taking an example of another position. So now we're trying to render an image at 120-degree azimuth, 10-degree elevation. This is a location where we don't have, again, a virtual speaker in our virtual speaker array. And in this case, we added another bit of information on the graphic, which in this case, the centroid of the distribution is actually not aligned with the intended location. We observed an angle of 15 degrees, and so we represented that with the arrow on the plot. In terms of the standard deviation, here we get a little over 30 degrees. So this is indicative of a source that is likely to be perceived as more diffuse than the previous example. Now let's move on to an example of using the second metric, the Jensen-Shannon distance. So this one requires a few steps, so I'll walk you through the steps. First, we compute the JSD between the impulse response of our system and every member of the test signal set, which again here is a reference HRTF dataset. And then we subtract that number from 1 and we plot it. This is what the map we're looking at here. And so on this map, if you have a very small distance between your intended, the output of your system and a specific HRTF, you would get a 1, meaning the distance is 0. Remember, we're showing 1 minus the distance. And then if it's very different, you could go all the way to 0. And And in this particular example, we're looking at a source that is at 90-degree azimuth and 0-degree elevation. And so we can see that in this case, we know we have a virtual speaker in that position in our system, so we expect it to perform pretty well for that position. And sure enough, we get a score of 1 here at a 90-degree 0 elevation. And you can see when you move away from that position, you compare to HRTFs on the other side of the head, you get a lower score. So that seems to work so far. Next, we compute what we call the angular distance map. This is strictly based on geometry, and it's just saying looking at my sampling of my HRTF database, for each position in that database, I'm going to compute the angular distance between that position and the intended position. Here, the intended position, again, was 90, 0. So if you're at that position, there's no distance. And as you go away to the other side of the head, you get more and more degrees of distance. And then on the opposite side of the head, you get 180 degrees. And then we normalize this from 0 to 1. So you would compute this map for, if you change the intended location you want to test, you would update this map. So from this distance measurement, we're going to extract again two numbers. So mean opinion score 3 is a location estimator. And so for that one, we look at, if I go back to the previous slide, we look at the maximum on this map. And then we look for that point on this map here, and we look at what's the angular distance for that. And so in this case, again, because we have a virtual speaker at 90 degrees 0, we expect it to work pretty well, and so that we would get a number of 0. And then finally, we compute our MOS4, which is computed by taking two maps I just showed, the distance, comparison from the output to each HRTF in the database, and then we look at the angular distance map. We multiply those element-wise and sum across all the elements, and that gives us our MOS4 score. And in this example, we get again a MOS3 of 0 degree. We expect that we will be able to do a pretty good job at rendering on target, and then MOS4 is 0.2329. The expectation here is that the smaller the computed value of MOS3, the more spatially accurate the rendering is likely to be. Again, this is focused on magnitude response. And then similarly, the smaller the computed value of MOS4, the least likely that the magnitude response error is detrimental to the compactness of the virtual auditory source. So if we had a very high number here, that would mean magnitude response is likely to introduce a problem with compactness of the source. Here another example. Can you grab the pointer again? So again, the top example was the target location of 90 degrees azimuth, 0 degree elevation. The second one is a source in front of you, so 0 azimuth, 0 elevation. If you remember, we don't have a virtual speaker in that location. And we get a MOS3 of 0, so we don't expect magnitude response to introduce a bias there in terms of direction, but we get slightly higher MOS4 score than the previous example, which again makes sense because here we know in this case we're using VBAP, we're panning between two virtual speakers to create this image. And so it's sort of expected that that image is likely to be perceived more diffuse, and hence the higher MOS4 score. So to recap on what we just talked about. So first, we introduced the problem, which is about evaluating magnitude reproduction accuracy of spatial rendering engine. Again, this could be the context, could be your tuning a rendering engine, trying to decide between different options, or making sure you're improving as you're tuning. Or maybe you're trying to decide between different algorithms, different architectures. It could be deciding on the number of speakers in your virtual speaker array. We discussed the potential approach and presented one that combined a perceptual transform and two error computation metrics. I illustrated that with some examples, which again you can find in the paper. And our system puts 4 figures of merit. MOS1 and MOS3 indicate the contribution of magnitude response reproduction errors to localization bias. How likely are we going to introduce a sort of an angle error in the perception of position? And then MOS2 and 4 indicate the contribution of magnitude response reproduction errors to localization blur. So there is more a sense of the impact on the effect on the perceived diffuseness versus compactness of the source. Potential next steps. Of course, we want to verify and tune this metric using critical listening. So we want to make sure that what we're seeing here correlates, even though at first, it seems like it's providing results that are encouraging. We need to confirm that with some more careful critical listening tests. That may also help. We may end up, based on that, refining a bit the metrics to map better to the perceptual listening experiment. It may be useful to combine those figures of merit into a single score. Again, if you're using this to help you make a decision between different algorithms or different tunings, in the end, here you end up with 4 numbers and you need to make a binary decision. So it may make sense to try to combine those into a single number. In this particular example, I'm not sure if I made that clear, but I used the same HRTF set to build my virtual speaker array as I used as my reference HRTF set. Of course, that's not necessarily required. You may want to consider using a different HRTF set. For instance, if you're trying to compare to listening test the data, you may want to use personalized HRTF of an actual listener to see how well it translates for that particular person. And then, of course, this was all focused on magnitude response. So there's other aspects such as ITD or more generally interoral excess phase difference that we need to be accounted for. And here we sort of made the assumption that those were addressed separately, but expanding the analysis to include those would be a benefit. And with that, I thank you, and I think we have time for a few questions.
All right, everyone, you'll see the raise hand icon on the right side of your screen. If you'd like to ask a question, please go ahead and hit that. And the first question I have is Leo. Go ahead and ask your question, Leo.
Well, I'm very sorry. I didn't actually mean to raise my hand, but thank you for the talk.
No problem.
All right, David.
Yeah, so if there are no other questions, thanks for the talk, Remy. It was really interesting. I wanted to ask, when you presented the different examples for MOS1 and MOS2, the example for the non-ideal example was showing some kind of a broken image, as if there were like 3 sources. In this case, I think it could be interpreted as a wider source or something that is perceived as multiple sources, as phantom sources. I just wanted to hear your thoughts about it and how can it be quantified?
Yes, and again, I want to stress the fact that this is, we're looking just at magnitude response here, so we're only looking at part of the information, but yes, the idea is that the sort of broken image as you described
Excuse me, sorry guys, please make sure to put yourself on amplify.
Thank you, sorry about that. Yes, so a couple of things. If we go to so this plot, I'm sure the plots I'm showing right now those are the ones using the GSD approach. There, if you see hotspots away from your intended location, so if we look at the bottom picture there, we're trying to render a source in the front of you. But if you see a hotspot, for instance, on the opposite side of the head, that could be indicative that this system is very likely to introduce front-back reversal issues, for instance, where if there's a lot of similarities. Someone is saying I'm not amplified. Okay, hopefully you guys can hear me now. I was amplified, okay. So if you see hotspot in this particular representation, if you see a hotspot away from the intended location, that could be a sign that there's a risk of hearing the location, the source coming from the wrong place. An example would be if you have a source that's meant to be in front of you, and the way you're rendering has a lot of similarity with HRTFs in the back of your head, where you're likely to get front-back confusion, because in this case maybe ITD isn't enough to help with that, avoiding that confusion. And yes, in both cases, whether you're looking at JSD or the other, the elastic neck approach, essentially the fact that we don't have compact hotspot in the middle here is a sign that magnitude response is likely to the errors in reproducing magnitude response are likely to introduce to make the source more diffuse. So I hope that helps answer the question.
It helps, and I was just curious to hear if you have any thoughts about how to measure how broken the source can be perceived.
Well, I think this is where comparing to doing a bit of critical listening could be useful, so that we can have a more perceptual mapping of those numbers I mentioned to say perceived source size. Right now this is we're looking at the standard deviation in this data, but we're not necessarily saying, oh, the source will look like it has this angle in terms of perceived size. So that there's potentially, I think, room there for tuning the model based on doing critical listening and comparing to the impression from the listeners.
Thanks. Yeah, we are having similar thoughts about similar questions that we are trying to solve.
David, could you also amplify again? Sorry.
Oh, yes.
Thank
Sorry. I just wanted to comment out that I'm happy to see that more people, more researchers in the community are working on trying to solve these examples. So it's great, Remy.
Mm-hmm.
Thanks.
Thank you.
Do we have any more questions?
So let's thanks again the speaker.
Oh, we just
Thank you so much, Remy.
got one more question.
Wait.
Yep. Great. Even
Osher,
better.
Go ahead.
Yes.
Yeah, hi. Can you guys hear me?
Yep.
Yes.
Hi, Remy. Yeah, thank you for your presentation. I was wondering on MOS 4, when you move from a target's direction lateral, I think 90 azimuth, 0 elevation, to forward direction. Maybe I missed that, but do you have any idea as to why MOS 4 goes up?
Yes. So this goes back. So you have to remember, in this case, we want the lower the score, the better, right? So if the score is lower, that's indicative of the magnitude response likely to not introduce bias or diffuseness in the source. But if I go back to my virtual array here, for the source at 90 degrees azimuth and 0 elevation, I apologize. I changed the slide on my side here, but it didn't update on the screen. So in our virtual speaker array, we have a virtual speaker actually at that position at 90 degree elevation, 90 azimuth, 0 elevation. So we get, and we're using VBAP. So essentially, when we render at that position, we're using that HRTF directly. So we get we expect that to work really well. When we try to render the source in front of you, in this particular setup, we're using panning between two speakers, one slightly above level, one slightly below. I think it's 10 degrees up, 20 degrees down, or something like that. And so we're essentially using a phantom image. And so we expect there that would introduce a little bit of error in the magnitude response. So that's where that came from. And we use that as an example, just illustrative example. All right. Well, if there's no more question, thank you very much, everyone.
Great, thank you, Remy. And we still have 2 more minutes, so let's allow everyone to take a small break, and we'll start in 2 minutes. Hey, Tamzid, feel free to go to the stage. Oh, okay.
So should I go on air and loudspeaker?
Johannes?
Hi, Tamzid.
Hello. Hey, yeah. Can you hear me?
Yes.
Yeah, we can hear you.
Yeah.
Yeah, you might want to check and see, are you at the first slide on your deck?
Oh, okay.
Are you advancing on another device? Are you using the in-VR browser, Tamzid, or are you?
In VR browser, yeah.
Okay.
Yeah.
And do you see it okay, or is it coming up?
Yeah. Is it not from the beginning?
Yes, I think you're on the first slide. Perfect.
Mhm.
Yes, I can see it as well.
Yeah, I was actually testing it on the audience side.
You
Bye.
gonna sleep?
And then we will
It's pretty late at your place, right?
resetting of the space.
Sorry, can't hear you.
A few minutes.
It's pretty late
Mhm,
at your
okay.
place, right?
Okay, thanks.
Yeah, it's 6 a.m. man. It's pretty early.
Yeah, you should go to bed.
Yeah. I'll see you
All right,
normally.
man.
Alright, see
Have a
you.
good night.
Bye.
Okay, let's
See you
where's
tomorrow.
Dustin?
Yeah, see you.
Bye.
Bye.
It's probably resetting the other spaces, other rooms.
So we should just leave it.
Okay, Dustin, if you can hear me, I think you're probably resetting the other spaces, the other rooms. Oh, there you are.
Right behind you.
Yep.
I just reset the 2 other rooms.
Okay, good. You want to go ahead and just reset this one then too, and then I think we'll just do a check here and see. Also, yeah. Also, you can check then to see if the live stream is good. Yep.
Hey.
If you want, you can take the time to organize the slides and everything, so it's convenient for you. You find the laser pointer underneath the podium.
Okay.
If you prefer to use your right hand for switching the slides, I would suggest to use the left hand for the laser pointer.
So just a reminder for Tamzid, David, go ahead and check that you're on air on your host tools,
Mhm.
and also that your voice is amplified for the starting.
Are we
And
good
we're just
to
gonna-
start?
Let's just verify that the live stream is working. Let's see if that's going to be
Yeah, okay.
still on
It is loading.
on the view.
Yeah.
I think it's fine. Is that correct, Dustin? The live stream?
It is still loading on my machine.
Yeah, I'm still checking it.
Okay.
So just give us a sign, Dustin, whenever you're ready. Can we start, Dustin?
Just one more second, sorry.
Okay.
Okay, looks good. Go ahead.
Okay, great.
Should I start?
So, yes. Okay. So thanks for staying with us. I know that for people from outside of the West Coast, it becomes really late. For the third talk, I'm pleased to present Tamzid. He is from University of North Carolina at Chapel Hill. He will present his work on estimating anthropometric feature using sensors on headphones for HRTF personalization, which is of course very relevant to the work that we are all doing. Yeah, Tamzid, the stage is yours. Please go ahead.
Hi everyone, my name is Tamzid Islam. I'm a fifth year PhD student at UNC Chapel Hill. So this project was done during my internship at Microsoft Research with Ivan Tashev. So the title of my project is Anthropometric Feature Estimation using Sensors on Headphone for HRTF Personalization. So this is the outline of my talk. First, I will briefly talk about HRTF, then about my proposed solution, then the data collection process, and after that I will talk about evaluation results. So when we hear sound and try to figure out where the sound source is, we rely on acoustic cues that are embedded in the heart sound, and these acoustic cues are dependent on two factors. One is the source azimuth elevation or the source location, and another is the sound from head, also an outer ear characteristics are known as anthropometric feature. And head-related function or HRTF encodes the listener-induced changes, and so this is the acoustical transfer function between the sound and the ear canal. So HRTF is very important for spatial sound rendering. Imposing HRTFs onto monaural sound and playing back the result over headphones allow for positioning virtual sound sources at arbitrary locations, thus making the sound binaural. And it has applications from game sound rendering, live streaming, concerts, and virtual reality. So current solutions for HRTF personalization on anthropometric measurement or measurement of HRTF from chamber or interpolation from acoustic cues such as interval delay or IPD. But all these approaches require additional hardware such as measuring tape for the anthropometric feature or using scale to measure users' anthropometric feature, or recent approaches uses 3D depth such as Kinect to get the 3D scan of the user and then estimation of ITD and HRTF. Sorry. So our goal in work, we want to relieve the user from using any additional hardware for anthropometric measurement, which can be used for ITD estimation. So our target is to use the sensors integrated with the headphone to sense anthropometry such as head width, height, depth, and circumference. So this allows us to estimate ITD, an important cue encoded in the HRTF. And so our proposed approach can estimate this listener-induced listeners and in real time and provide seamless transition when the headphone is passed from one to the other. We are using micro surface headphone, and this headphone already has all the necessary sensors for our algorithms, but for quick prototyping, we added extra sensors to the headphone. So we added a microphone and also IMU board on the right side of the headphone. And this IMU board has gyroscope, accelerometer, and magnetometer integrated to it, and the sampling rate for the IMU was 100 Hz. So we propose 3 approaches for 3 different modalities. And then we also propose a fusion algorithm. So first I will talk about our first, that is the sound signal propagation for anthropometric estimation. So the main idea for sound signal propagation is that transmit a sound from one side of the headphone and record it in another ear. Then the time delay between the transmitted signal from one ear and on the other ear will depend on the distance it travels. And this propagation will encode the information about the user's head circumference. So the steps these are the following. So first we send a stereo signal to the headphone, a linear chart played in the right channel. We use it for calibration and we call it TX calibration. And then we play another linear chart on the left channel and we call it TX response. So when the TX response travels to the right side and get recorded on the microphone, it gives us the record information about the time delay between the transmitting and receiving. So the next step is denoising. So we want to, because our played signals frequency, so we use a bandpass filter to remove other components from the recorded signal to remove the noises. The third step is the calibration. As the TX calibration is played on the right channel and we are also recording on the right ear with our microphone, so the time delay between the propagation should be negligible because they are in the same place. But still there is a considerable delay that we find due to synchronization discrepancy between the recorder and the speaker. And this system-induced delay happens because of the system calls. And to estimate this delay, we use cross-correlation between the transmitted and received signal, the first chart. So the calibration and RS calibration, we cross-correlation and estimate the synchronization delay, which requires signal shift to align the signals. So the time delay between the left earphone and the microphone is estimated using the cross correlation. So this step gives us the summation of system-induced synchronization delay and the signal propagation delay measured in samples, and the propagation delay between the left earphone and the right earphone and the right microphone on the right earphone encodes information about user's head circumference. So if we take the cross correlation between these two shift, we get our desired estimation of the time delay between these two signals, and that includes the information about user's head circumference. So gives us the delay in terms of samples, and from that we can estimate the delay time of the signal propagation, and that gives us estimated distance. So we use nonlinear curve fitting for further smoothing of prediction. The second modality that we use is magnetic field propagation. So the idea behind is that, I'm sorry, every time I'm changing the microphone, it's creating some noise. Just 1 minute. Yep, sorry everyone. So the speakers placed in the earphones consist of magnet and coil, and so when we play a sound through the speaker, coil variable magnetic field, and this magnetic flux density is inversely proportional to the distance. So the magnetic sensor, which is mounted on the right earphone, that is at a constant distance to the sensor, because the sensor is also mounted to the right earphone, but the distance to the left earphone depends on the head width of the listener. So when the head width will change, the magnetic density on the between the magnetometer and the left earphone will also change. Therefore, the RMS of the signal that we see will be dependent on the user head width. So the further the speakers are, the RMS will get lower, as the magnetometer is only on one of the earphone. So we use this principle for estimating the user head width. So these are the steps for that. So first we get the signal's magnitude, 3 axes that we have from the magnetometer, and get the magnitude from those 3 signals. Then the magnitude produced by the headphone speaker is masked by noises and magnetic interference due to presence of magnetic objects in the environment. Apply a bandpass filter to remove the inference outside of probing signal's frequency band. And this step also takes care of Earth's magnetism. Then even after the bandpass filtering, the magnetometer signals are still very noisy. So to suppress the non-correlated signals and increase the signal to noise ratio, we use synchronous detection. The idea of synchronous detection is to multiply the already prepared monotransmitted signal with signal to amplify the modulated segments of the received signal. And last step is the feature extraction. So we use the RMS value for 2 received signals and also their ratio between them and the RMS as our feature, because this difference between this signal RMS will give us estimation of the user's head width. Once we those features, we curve fitting. We use 2 methods and evaluate both of them. We use curve fitting, and then we also use extreme learning machine, which is a type of neural network. So that I will later. So we use these 2 methodology to extract and feature using magnetic field propagation. So the last modality we explore is head movement tracking using IMU and gyroscope. So with IMU and an accelerometer, we track human head rotation and exploit the relationship between linear acceleration and angular acceleration. So horizontal head movement can be modeled as a circular motion where the center of the circle is the center of the head and radius is half of head. So for any circular motion, there are 2 types of acceleration associated. One is centrifugal or centripetal acceleration that denotes the change in direction of the tangential velocity. And another is tangential acceleration that defines the magnitude of tangential velocity of an object. So in this figure, we can see their directions and which relate to the head movement. And there is a kind of acceleration related to circular that is called angular acceleration. So angular acceleration is defined as the change of angular velocity of the moving object. And the relationship between the angular acceleration and tangential acceleration is presented here. So we can see that AT, tangential acceleration, equals to alpha times radius. So alpha is the rotational acceleration here. So radius is the user's head width. So we exploit a relationship to get the user's head width from movement tracking. So the steps for that are first we use a moving average window for denoising the signal because the accelerometer and gyroscope both have a lot of noises, high frequency noises that we want to remove from the signal. Then the next step is that due to the orientation of the IMU in our prototype, linear acceleration along y-axis contains the tangential acceleration, but due to the tilt of human head, linear acceleration also gets affected by the acceleration due to gravity. So we use a de-reckoning module to extract the tilt of the head from the gyroscope, and then we remove the effect of gravity by subtracting from the accelerometer readings, and then we get only the tangential acceleration from the. And the third, rotational acceleration estimations we get from the gyroscope gives us the rotational velocity. So if we take the first derivative, then we can estimate rotational acceleration from there. And once we have the rotational acceleration, we can use this between the rotational acceleration and the tangential acceleration to estimate the radius. which is correlated with the user's head width. So we use a curve fitting methodology to estimate movement and RTD scaling factor from this value. And now I'll talk about the fusion algorithm. So in the fusion part, what we do is we extract the features from all the modalities, the 3 modalities that I have shown, and the input feature vector contains information from all these modalities, so which make the representation robust as it does not rely on a single sensor. And then we feed them into a learning machine network, so which is regress the anthropometry of the user. And the extreme learning machine, or the ELM, consists of just one broad hidden layer of neurons. And we use ELM because it has better generalization performance with limited training data, because we work with our own collected data. So our data set was not a lot, so we used ELM for its generalization. So now I'll briefly describe about our data collection procedure. Citation signals that we use. So as sound signal, we use 20 to 22 kilohertz linear chirp because we wanted to be in inaudible range, because the steps we envision them as non-intrusive, and the duration was 2 seconds. So we want to make it very fast, and it was a stereo on both right and left and each signal played 10 times. For magnetic signal, we went to 8 to 10 hertz because the that we are using had a sampling rate of 100 hertz. So we could not from 8 to 10 hertz for because they was inaudible. And here the duration is 2 seconds, and it is also played 10 times. And for head movement tracking, the users were given instruction to move their head. So there is some signals to particular direction, so the user move their head to that particular direction. And ground truth, we collected user head width, height, depth, and circumference using scale and measuring tape. And the sound signal, as I described before, that we recorded with a microphone, and the magnetic signals were recorded with the magnetometer that we placed on the INU board. And the head movement tracking was, and they both had sampling data. And this is the data distribution for the users. And so we had 35 participants, and the distribution span from 15 centimeter to 18 centimeter in terms of head width. Based on our literature review, this span was pretty reasonable. Now I'll talk about the evaluation part. So as the evaluation metric, I'm using root mean square because it's a regression problem. So I'm using root mean square error as metric for evaluating the anthropometric features. And I'm also showing the Pearson correlation coefficient between the estimated and ground truth value. So to describe the statistical relationship of predicted and ground truth value. And during training for the ELM network, we use one-out policy. That is, at 10 participants, then we will leave. If we have 35 participants, then we use 4 as training and 1 as testing, and we did it for user. So each of the user set as case like this. So first, talk about the RMSE value for the anthropometric feature estimation. So you see that for head width, in the lowest RMSE we get is with the fusion algorithm, and because you estimated values from other modalities and aggregating them made the fusion algorithm more robust. And from the single modalities, we see that the head movement tracking did better than the other, because head movement tracking, because sound signal and magnetic signal are from the noise, but in the movement tracking we do not have that. For head height, all of them because none of the modalities explicitly sensing the head, so they are bit higher for all the modalities. For head depth, we see that the fusion is doing better than the others, and the head movement track. So here you see that all the single modalities are also doing better, and they are doing kind of same, but head movement tracking was the best. And for the head circumference, we again see the fusion did improve over single modalities, but from a single modality, see that sound signal propagation did better because sound signal propagation was seeing the head circumference explicitly. Then we have presented here the Pearson correlation coefficient, and it is consistent with our MC value that fusion has correlation with the output value for all the anthropometric features, and likewise the head movement tracking is doing well on head width and height, and for head circumference the sound signal propagation is doing better than other modalities. So we also present based analysis, so where we divide the heads width in clusters, so based on their range. So for 15 to 16 we assign a small cluster, for 16 to 17 medium, and 17 we refer to cluster. So we see that the classification accuracy, so sound signal propagation has 35% accuracy, magnetic field propagation has 53, the head movement tracking has 59, and the fusion has 67% accuracy. So one thing is that all of these modalities struggle with the big head, but the fusion-based approach misclassified them all as medium, so most of them as medium. So the error resolution here was around 1 centimeter, and the fusion also did detect all the perfectly. So we can see the improvement of using fusion-based algorithm instead of only a single algorithm. So yeah, here is this evaluation of all the anthropometry, and we see that the fusion-based approach is superior than using single modalities. And we also did an experiment with ITT scaling factor estimation. We estimated the ITT scaling factor using these extracted features, and we see that for that also the fusion had better accuracy in terms of RMC and also Pearson coefficient. So we propose a system to measure anthropometric feature for ITD estimation using sensors on headphone. We proposed 3 different approaches for 3 different modalities. We designed sound signal processing algorithms for anthropometry estimation, and we developed a data collection pipeline and collected data from 35 users. And we compare different approaches and fusion algorithms using real data. So this is the whole presentation. Thank you. If you have any questions, please go ahead.
All right, go ahead and hit the hand raise button on the right-hand side if you have any questions. And looks like Remy does. Go ahead with your question, Remy.
Okay, can you hear me?
Yeah.
Yeah. Thank you for the talk. Yeah, I like your approach of using data from multiple sensors. I was wondering, since you're using, it seems like a machine learning approach to combine the information.
Yeah.
Have you considered, I guess, just using machine learning to solve the broader problem? It's instead of kind of the combination of traditional signal processing and machine learning.
That's a very good suggestion, and I actually did try to feed the signals into machine learning algorithms, such as I experiment with RNN. But the problem was that we did not have a lot of data. So we had 35 people, and for each of the people we had 10 samples. So in general we had 350 samples. So the network was kind of overfitting. So we saw that the network was generalizing, it was memorizing the data, and it was not generalizing. So yeah, we did actually try this, but yeah.
All right, thank you.
All right, and David?
Yeah, thanks, Tamzit, for the great talk. Just following up on Remy's question, did you consider, I think you considered evaluating the effect of the estimated features on how accurately you can represent the ITD? Is it correct?
Yeah.
You showed something like that in one of the last slides. Can you give more details about that? I think this is like the most interesting part here, to understand how accurately we can actually estimate the ITD. And the units here are still centimeters, for example, for the RMSC. I guess that for the ITD row, it is something else.
Yeah,
What are the units here?
yeah. So this I think this should be correct. So for the ITD, we actually did not estimate the direct ITD. So what we did was we followed one of the papers in the previous years, estimated ITD scaling factor. So if we have a from by averaging ITD from a lot of people, this scaling factor would describe how much deviation is the ITD of the current user from that average ITD. So we predicted this scaling factor. So instead of predicting the direct ITD measurement. So this is and this RMC value for that scaling factor. And I can compare that how correct is this. So we had a 0.045 ITD scaling factor RMC using our approach, but in the paper that uses Kinect for estimating this ITD scaling factor, 0.033 scaling factor RMC. So this is the comparison.
Can you repeat the numbers again, Tamzid? Here we get 2.045, and with the Kinect camera, how much was it?
Sorry, so here we have 0.05, and using Kinect camera 0.03.
Okay, and how will it reflect on ITD values? Do you have a sense of numbers just to emphasize how significant these results are?
So actually, we did not go through the step because we did not do any kind of like user subjective study the generated estimated ITD and all. So, but reference point of the Kinect based paper, because Kinect is using this camera and getting the 3D head scan and getting soft data Kinect, but here we are only using data, so we kind of want to reach that value, but kind of like near, but not as good as that.
Okay, great. Thanks for this answer. Do we have any other questions?
We do. We have. Sorry. Yes, we do. We have one more, or two more now. So Keith, go ahead.
Hi.
Hey.
Hold on just 1 second, Keith.
I'm unmuted now. Okay, great, thank you. Just about the ITD scaling factor still, I think to sort of
Hello.
Oh, we lost you again, Keith.
I don't know why I'm being muted and unmuted and muted and unmuted, but...
All right, you should be good now.
Okay. I don't know where I was, so I'll sort of start over. I'd ask a similar question, maybe to restate, because I didn't quite understand the answer to the last question. To state in a different way, what do you think is the range? So ITD scaling factor, like what is the, what are typical ranges for that from a human? I think like no scaling is 1, right? And then how low does it range below, and how low does it range above? And so when we see an RMSE of like 0.045, is that like extremely small, or how does that relate to the population-wide range of ITD scaling factor?
Yeah, so one thing is that let me just go to that. So I showed a slide with the clustering based approach, right? So we had these 3 clusters, and our target was that if we can like estimate that if we can also get the clusters of ITD scaling factor based on that is correlated with head width, then we can get an estimation of that range, right? Because in general, I could not find any study that had this that did this kind of analysis of like how close the ITD scaling factor has to be to get a very good experience. So one approach could be is that to correlate these clusters based on the head width and the ITDs, and if we can estimate these clusters correctly, then we are doing pretty well. So to answer your question, actually, go through that kind of study.
Okay, I see. Great. Thanks. That's my question.
And it looks like Stefan, go ahead with your question.
Hello, can you hear me?
Yes.
Hello.
Yeah, we can hear you.
I couldn't quite hear you before, but I'm just wondering, did you measure the subjects with the physical measurement, and do you know what the error between the physical measurements and the calculated measurements is?
The physical measurement, yeah. So the ground truth value we calculate is from the physical measurement, and the estimation, and we use these RMSE values to compare the estimated value with that physical measurement values. Hello. Hello.
Thank you.
Yeah.
I was muted again. Thanks.
Okay.
Any other question? Yeah, I think it's a good sign.
Any other questions?
The amount of questions just emphasize how interesting this topic is for the audience.
Yeah.
Do we have?
And
any
I'm
more
sorry
questions?
because my microphone was in kind of like the slide change button. So every time I was changing the slide, the microphone was getting picked up, and I have to so that was kind of interrupting my talk actually.
Yeah, we could hear you fine. The amplifying my voice makes it redundant to use the microphone, so it was all fine.
Okay.
Do we have more questions? Okay, so let's thanks the speaker again. It was a really nice talk, Tamzid. Thanks.
Thank you everyone for the questions.
And I guess it's a wrap for today. Thanks. This was the second session of the paper session in ASMR. See you all tomorrow.
Thank you, David. And I'll also just tell people that you're welcome to go over to AVAR lobby and chat. We put that on the schedule kind of late, but you're welcome to go over there. And also there is about half an hour or 25 minutes left of the workshop session over in AVAR workshops. You're also welcome to pop in there. All right, see you soon. Thank you. And thank you all presenters for this great session.